Hi, let's continue the analysis of this active load amplifiers. So in the previous video we were trying to find out what is the gain and R out of this amplifier. Of course we have considered the specifications as these, and upon finding the WBL of this transistor, it comes out to be a ratio of 247.7. So with the assumption of length of this as 10 micro, and the width of first transistor becomes this, and as we saw in the previous case, so the WBL of 2 will become 495.5, and of course since it is PMOS transistor, we are taking the magnitude of VDS as 0.9. So why it is 0.9? Okay, as I explained in the previous video. So if you want to have the output voltage at mid of VDD, so if this is 0.9, this is 1.8, then VDS becomes, VDS is actually minus 0.9. That's why we are writing VDS as magnitude of VDS as 0.9. Similarly, VGS is 0.6 magnitude, VTO is also 0.6. All the magnitudes of PMOS transistors are this. Their actual voltages are negative. That's why since VGS of PMOS transistor magnitude is 0.6, the actual voltage is minus 0.6. So if you actually look at the way how the terminals of gate and source are connected, if you just look at this circuit itself, if you carefully look at what are these, we know that this is source, this is drain, this is gate. If you see the source is connected to 1.8 and gate should be at 1.2, so that VGS becomes 1.2 minus 1.8, which is minus 0.6. So that's how you are getting this VGS as minus 0.6, which is nothing but 1.2 minus 1.8. So this is how we got this as 1.2. Okay, these are the values of GM. AV expression from our theory, we can write it is GM1 into R01 parallel R02, which comes out to be 496.6 volt per volt, and the R out looking from here should be R01 in parallel with R02. If you look at the values of R01, R02, because R01 is given by 1 over ID into lambda, R02 is also 1 over ID into lambda, because same ID flows, and since we are assuming the same value of lambda, that is 0.01 for both transistor, so then these two values will be same, so it's equal to 100K. So their parallel combination is 50K, and let us verify those things in simulation result, so which you can see it by doing a DC analysis. If you run it now, go to this view and see the error. If you can see here, this is ID flowing in both the MOSFET, and VGS is 0.6 and minus 0.6, and VDS you can see it's almost 0.9 and minus 0.9, and threshold voltage is 0.4 and minus 0.4. This is for NMOS, this is for PMOS. VD SAT is 0.2, that's what we assumed here. You can see here, this is VOV, the overdrive voltage, and the GM is 10 millisiemens. So for both, of course, we are not worried about the GM of M2, that doesn't come into picture of our design. So we are looking at the GM of M1, which is 1 to 10 power minus 2, which is nothing but 10 millisiemens. So theoretically it comes out to be 9.95 millisiemens, which is close to 10 millisiemens. So upon doing the, of course, how do we get the R0 in these? So R0 is actually 1 over GDS. So if you just, of course, you can just have a look at this. So usually, of course, R0 is given by 1 over the conductance between drain and source. So what is this? So this is 1 over, so you have it as 9 point. So this is actually, if you just go back and see, this is GDS 9.91 e power minus 6, 9.91 e power minus 6. If I find 1 over that, it is 9.96 e power minus 6, 1 over that is 100.4 kilo ohm. So this is the resistance what I have. that's what is expected from this simulation. So we actually expected a resistance of 100k. This is 100k. We are getting it as 100.4, which is approximately 100k. So from this we can make out the gain that is coming out to be from these values, that is GM into R01 parallel R02, so is 504. So let us verify the same thing over here. So what I'll do is, let me do the transient analysis. I'll do transient analysis, and then this is the timing, so that I can see 10 cycles. Why 10 cycles is because I have kept a frequency of 10 kilohertz, and let me run this now. If you can carefully see here, we actually have two outputs, two nodes. This is output, this is output 2. Let us spend some time with this particular circuit what we have now. So let me just name it as RL. Let me name it as RL. Okay, just says that it's a load resistance. This RL, I'm varying it from, okay, I'm just using it as a parameter, having two values for this resistor. First value is 10 mega ohms and the next value is 50k. So let us spend some time. Okay, why I just kept it as 10 milli ohm and 10 mega ohms and 50k. So if I just see this analysis, so you will get some idea. So the purpose of making it this. So if you see this, so carefully see this. Is this an amplifier? This is an amplifier with input port and output port. So this is input and this is output. So actually the black box of this amplifier can be represented as a input resistance, a voltage gain source, and then you have a R out. Now so we have a input voltage applied here. So how do we find R out of an amplifier in simulation? So now we have to find out what is the R out of this amplifier in LTSPICE. So let us discuss how do we do that. So to do that, so let me just see here. So this is my amplifier. I am applying some input voltage. So let me know what is the output voltage here. So this output voltage can be given as A0 into Vin, which is this voltage source multiplied by RL. Of course, this is actually current flowing through this into RL is your V0. If I actually write what is V0 is equal to, it is I into RL. But what is I here? This I is nothing but current flowing through this, which is nothing but this voltage divided by the sum of resistance, exactly this. So this is my I. So I can replace this I by V in into A0 RL by RL plus R out is my entire V0. So now I don't know this R out now. So I am supposed to find the value of R out. For that, let us first measure the output voltage with this as a very large value, which I set as 10 mega ohm. When this is 10 mega ohm, so let us come here and then substitute. So this is V in, you have some A0, assume that this is 10 mega ohm and this is again 10 mega ohm, and you have R out which will not be 10 mega ohm. So as per our expectation, now this should be 50k. We know that it is R01 parallel R02, which is 50k. If you actually do this, so what is V0 now? V0 is equal to V in into A0 10 mega by 10 mega, because this plus this is almost equal to 10 mega. This will go off. So what is V0 now? V0 is equal to V in into A0. So this is my gain I'll be getting. So gain of the amplifier will be, okay, let me write it as AV. Let me write it as AV here. So V0 into, V0 is given by gain times the input voltage. Gain times the input voltage. Now, first value, let it be very large value. I am supposed to make it infinite. Since infinite is not possible in simulation, let us give a very large value. In the second case, make this RL equal to R out. when you make this RL equal to R out on the same thing, so what is V naught now? V naught is equal to V in AV multiplied by what is RL you are looking at? Let it be R out, and then is this again R out plus R out? So is it not becoming V in into AV by 2? That is, if this resistance becomes equal to the output resistance of the amplifier, the output voltage will be half of the maximum voltage. So here you can see there was a maximum voltage available when the load was maximum, or it's like when the load is open circuit, you had some voltage which is usually the maximum now. Now when you keep reducing the resistance, this voltage V naught is keep reducing. So when this resistance becomes equal to this resistance, this will be equal to half of the previous value. That's what we are trying to do now. Since we already know what is the output resistance of this amplifier, which is R01 parallel R02, which is equal to 50K, in the simulation you can see I am putting two different values of RL. One is 10 mega ohm, other value is 50K. Why I am just putting this as 50K? It is to have this condition. It is to have this RL is equal to R out. When RL becomes equal to R out, the output voltage expected here is half of this value. So you had some output voltage here when RL was 10 mega ohm, and when this RL becomes equal to R out, I will have the output voltage which is exactly equal to half of the previous output voltage. So if you measure the output voltage here or here, in the first case it will be maximum output voltage, in the second case you will going to have exactly half of the previous case. So let me run now. Okay, before that, first let us verify the gain of this amplifier. So what I'll do is I will make this only one value. Okay, let us do this for, I'll just make it only one value. I want to find what is the gain of the amplifier. So let me run now. Okay, now it is, because param requires two values, so let me actually take out this, make it as 100 MEG itself. Let me take out that dot step parameter itself. What I'll do, I'll comment this. I have commented. Fine. Now let me run this. So what actually I have now is, I have a load of 100 mega ohm. 100 mega ohm is like open circuit. It is not coming in parallel with, of course, even if it comes in parallel with 50K, that is almost equal to 50K. Now if I measure this output voltage, so let us find out what is the gain of the amplifier. So what I'll do now, so okay, let me just take out this also for the time being. Let me take out this also. This is what? This is my output voltage. So let me also take the input. So where is input now? This is the input. Okay, let us put them into different pins because it is amplified by too much. So let me just put it in different pane. Let us put the output here. This is my input. Let me change the color to red. Fine. Let us measure what is the input peak to peak. So input peak to peak is, so as we know, it is 0.1 into 2. I think it is 200 microvolt. So let me just go here. Sorry. Let me go to this and find out how much is the amplitude. You can see this is 1 millivolt. So this is 1 millivolt is the input voltage. So peak to peak will be 2 millivolts. Sorry, here. Sorry, this is 1 millivolt. So 1 millivolt, sorry, 0.1 millivolt. 0.1 millivolt is 100 microsecond. Sorry, 100 microvolt. So peak to peak is, that's why you have a peak to peak of 200 microvolt, which is the input. So this is the input now. So input, you can see, let me just zoom this. Now let me make it here. I'm there. This is, you can see it's almost 200 microvolt is the input. Let us see what is the output peak to peak. You can observe one thing. So is the input voltage increasing like this and coming down? Is it exactly going in the opposite direction? So this is what is that out of phase, the sign negative. So let me try to find out what is output voltage peak to peak. If I double click on that, both the cursors will come over there. You can see now this is my output voltage peak to peak, which is 100 millivolt. So if you carefully notice, let me just show you what is V naught peak to peak by V in peak to peak. V in peak to peak is actually 200 microvolt. This is actually 100 millivolt. So this volt will cancel. So what is this now? Is it not 100 exponential minus 3 divided by 200 exponential minus 6? Is it not 500? So since it is out of phase, it is a minus. So it has got a gain of 500. As per our theoretical knowledge, we are supposed to get 497 or 504. So can you see, is the gain is in the order of expected value of close to 500? So I am getting a gain of 500. I am getting a gain of 500. So this is what with infinite load. So I have not connected any load now. So now the output voltage is 10 millivolt. So what I'll do now is, I'll do this now. So I will change this. So if you actually see now, so what I actually measured is, with this as very large value, I am getting what is V naught now. V naught is actually equal to, of course, V naught peak to peak is actually 100 millivolt with, so let me write it, what is V naught peak to peak with RL as 100 mega ohm is 100 millivolt. So let me now find out what is V naught peak to peak when RL is equal to R out. When RL is equal to R out, that is 50K. So I know that as per this theory, this should be equal to 50 millivolt. That is, peak to peak should be 50 millivolt. If it is 50 millivolt, then this resistance is equal to this resistance, or when this resistance is equal to R out, then only I'll get half of the output voltage than 100. So let me just, now how do I make that 100 mega to 50K? So that's what let me just undo here. So if I do undo, all those things will go there and then I'll get back. Okay, now this is fine. Can you see now? Either you can make it 10 meg or 100 meg. Let me make it 100 meg only. Now first resistance of this RL will be 100 mega ohm. I will get the output voltage. I will get the output voltage for 50K as my RL. Let me run now. Okay, let me not see the output voltage. Output voltage will not change. You can see output voltage is constant. It is overlapping on each other. So I'll take out the output voltage because we have verified the gain. Let me just delete the pane. I have deleted. Now let us see. What is this green plot? Green plot is for a value of RL is equal to 100 mega. The blue one, okay, let me change this color to, I don't know, can I able to change the color, reset colors? I don't know. Okay, let us, okay, now see now, I'll just, is this maximum at 100 milli? Now place your cursor here and then use the arrow key. This will come down here. Now come over here and then press the arrow key, you will get this. So am I now measuring the peak to peak of this output voltage when RL is 50K? Can you see now this is half of that 100 milli, which is 50 millivolt. So what does this actually mean is, when this RL, where is that? Here. When this RL becomes equal to R out, the output voltage that I'll get here or here will be half of the previous case when the RL is very large value. So now this says that the output resistance of this configuration, this CS amplifier with this active load is equal to 50K, which is true from our calculation also. Okay, let us move on to the next circuit. So I want you people to have a look at this design carefully. Just have a look. So now the load is a diode connected PMOS transistor. So I know that for a diode connected PMOS transistor, this resistance looking into the drain will be 1 over GM2 parallel with R02, which is approximately equal to 1 over GM2. So now look at the design part of it. Since we are assuming same idea of 1 milliampere and VOV of 200 millivolt and lambda of 0.01. So as in the previous example, so we will going to get the same value of W by L for this NMOS transistor, which is 247.7. With the assumption of this as 10 micrometer length, the width becomes 247 micrometer. On the same lines now, since this is shorted with this, gate and drain are shorted, so since we are assuming the DC voltage of this to be at 0.9, so this will become 0.9 and this is now 1.8. Now the VGS of this will become minus 0.9, or magnitude of VGS is 0.9. Please try to understand this one. You take a pause and then understand what is this. For MOS M2, the drain and gate voltages are at 0.9, whereas source voltage is at 1.8. So if I take the magnitude of VGS, then it is 1.8 minus 0.9, which is 0.9. But the VGS of this transistor is minus 0.9. So with this VGS as 0.9, VTO as 0.4 and this as 0.9, the W by L comes out to be 79.4. 79.2 will become, 1 second. Okay, now we found that okay, W by L of this happens to be 79.2. You can surprisingly see this for the same circuit when this was connected to some base, okay, some DC voltage where VGS was minus 0.6. The W by L was, if you can see, it was 495.5. You can see this W by L has drastically reduced to 79.2 because my VGS is too much. So VGS is now 0.9. So this is the change that will happen from the previous to this circuit. And of course, these are the dimensions of the second transistor, and corresponding, now you can see I am finding the GM of both the transistor because the output resistance of this is, or the R load, R out of this is R01 in parallel with 1 over GM2, and this is what is R02, which is 1 over ID into lambda 100K, and its GDS, that is 1 over GDS2 is this, which will be almost close to 100K, and this is what is the expression for AB, which is minus GM1 into R01 parallel with 1 over GM2 parallel R02. If you actually find out these values, the gain comes out to be very less, which is minus 2.5, and this is what is R out, which is R01 in parallel with 1 over GM2 parallel with R02. So this is what is the values. If you actually find this GM2, which is this 4 millisiemens, so actually 1 over GM2 will become 1 over 4 milli will be 250 ohms. So that's why this 250 ohms in parallel with 100K is almost 250 ohms. That in again parallel with this will become almost close to 250 ohms. Now let us see the simulation of this. So we will do the simulation of this circuit having these dimensions of the MOSFET with this as 0.6, and since these two are shorted, the dimension of this is 79.2, all those stuff. Let me go here. Okay, this is the previous circuit. Let me open the second circuit. So this is my second circuit. Now if you can carefully see here, we have this MOSFET having the same dimension as the previous case. This is 247.7 is the W by L, whereas the W by L of this is, you can see it is 79.2. Of course, 792 by 10 will become 79.2. This is the W bell of PMOS transistor. Why it is so less is because my VGS has increased from 0.6 to 0.9. Exactly minus 0.6 to minus 0.9. Now you can see we are again doing this. Of course, let us verify the gain of this amplifier, which is 2.5, with the resistance as a very large value, and then we will make the resistance equal to R out. We will see the output voltage is half of the previous case. So first let us verify the gain of this amplifier. Okay, to verify the gain of the amplifier, let us see what is the output peak to peak at 10 meg and what is input peak to peak. Of course, input peak to peak happens to be, since input is 100 millivolt peak, peak to peak will be 200 millivolt. So let us find out what is for the second circuit. So we are looking at this now. V naught peak to peak by V in peak to peak. So V in peak to peak is actually 2 times 100 millivolt. So this 100 millivolt is the peak, this is 2 is peak to peak. So let us find out what is peak to peak of the output voltage when this RL is very large, So that I'll come here, because first value of RL is 10 mega ohm. So let me run this. I will run this. Okay, let me just remove all this. Now let me see what is, okay, let me do, maybe if you want to verify the parameters of R, okay, GDS, GM, all those stuff, you can see here. I can just go here and then see. Let me verify the theoretical and the practical values here. Okay, what is, you can see it is 9.95 is GM1 of NMOS. You can see this is GM, this is almost 10 millisiemens. Okay, then this is how much? This is 4 millisiemens. Can you see this is almost 4 millisiemens here? Sorry, yeah, this is 4 milli. This is 4 e power minus 3. This is 1 e power minus 2. 1 e power minus 2 is actually 10 millisiemens. Can you see this is almost 10? This is almost, okay, these are the simulated simulation results. This is the actual calculation results, which are almost tallying. And I should get a gain of how much? Minus 2.5. Again, it is out of phase and minus 2.5. So to see the gain, let me do transient analysis. I will do transient with the time as 1 milli, 0 and 1 micro. Fine. Let me see 10 cycles. Let me save it and run. This is, let me see, is the recording going on? Yes, it's fine. Let me see the input. This is my input, and let me see the output here. Okay, what I'll do is, let me just put it in different planes. This is the output. See now, of course in the output you have two plots. One is corresponding to RL of 10 mega ohm. The second one is corresponding to RL of 249 ohm. So let us first verify the gain. So we actually found the input peak to peak as 200 millivolt. Let us find what is output peak to peak. If I see output peak to peak, see now this is one peak, this is the other peak. Let me just zoom this. So this is at the top. Let me just keep it at minimum. Can you see now it is 496 millivolt. So this is what is the value. So this is 496, this is 200. So 496 divided by 200 is 2.48. This is the gain of the amplifier. So I have a gain of 2.48 because I am expecting a gain of 2.5. So we are getting almost the same gain as in the simulation result. So now let us find out what is R out is. So R out happens to be 250 ohm theoretically. If I make this resistance equal to, that is, if whenever, let me just close this. Which one? Okay, let me close this. If I make this resistance, whenever this resistance equal to second resistance is 250 ohm, then the output voltage will be half of the 496. So what I'll do, let me go here go here. So now let me just click on this, click on this. See, now this is almost equal to half of the previous case. So that was, of course, it was supposed to be, how much is 496 divided by 2 is 248. I'm getting it as 242. Of course, output resistance slightly more than 250 ohm. Of course, it is in the order of few ohms. Maybe it may be 255, 260, but you are getting it very close to half of the output voltage. So output voltage earlier it was 496. Now it is half of that, because the load resistance now is equal to R out. So this is the like open circuit. This is with RL equal to R out. Because R out is not visible, so we are trying to measure R out by making this RL equal to R out, which is 249 ohms. 249 ohms. So let us see one more circuit. Go here. See this. So all these are now it's a question of analyzing the circuit. Spend some time with each of the circuit. This is a specification. This is VOV ID, from which I'll get a WBL of first transistor as this. So with the dimensions as length and width, and since we are using a resistance of 200 ohm, the VDS of this will become this is, of course, this is 0.9, and you have a 200 ohm resistance and a current of 100 millivolt is flowing. So then VDS2 will become actually 900 minus 200, which will be 700 millivolt, and ID2, since you are making this voltage, this terminal is shorted with the gate. So VG is at 0.9. So VG is at 0.9, whereas VS is at 1.8. So VGS of second transistor becomes 0.9. So substituting this as 0.9, substituting this as 0.4, and VDS as 0.7, I will get the WBL as 79.4. And you can see the R out of this is slightly different. The R out of this is, so looking down into the drain becomes R01. Looking up towards this, when you have a connected R2, is given by capital R2 plus R02 divided by the intrinsic gain. So this is what is the resistance looking up towards the load, R01 in parallel with this. This also comes out to be close to 249. So gain of the amplifier is almost, because in the previous case also I had a GM of 10 milli, and this is equal to 249. So the gain is still again the same. So let us see this. The only thing here is that I should be knowing what is the impact of connecting R2 here. So since I connected R2, that is going to have an impact on the VDS value. VGS still remains as 0.9. So this VDS has changed to 0.9. So this is my R out. Even though you have a huge change in the equation, but ultimately the value is almost equal to 249 as in the previous case. You can see it's almost 249. You can see the expression is totally different. Here it is R01 in parallel with 1 GM2 R02, whereas it's a totally different equation. But effectively the resistance is, because R02 is 100 ohm, this is like 200 ohm, this is like 100k, this is close to 100k, and this is, you can neglect this one. So this 100k will get cancelled with this 100k. You ultimately end up with this as 1 over GM2. So this effective value is still 1 over GM2. So that's why this R out is no change compared to the previous, even though you have a totally different circuit. So you can just go back to that circuit. Let me save this. Open the third circuit. Now this is the circuit what I'm looking at. Let me close this. Run it now. Let us compare with the input voltage. Gain should be gain we are looking at as this is my input, blue one. This is of course naturally 200 millivolt peak to peak. You can see this is almost close to 200. Let me zoom this here. Let me keep it exactly so that I can see the peak to peak. Can you see it's almost 200? Let me see it on the output. So output should be 2.4 times. So this is 200 into, okay, this is what is V, of course AV is given by V naught peak to peak by V in peak to peak. If you just see here, so this is like, okay, 200 millivolt. Let me see what is output. If I see the output is, let me just double click on this. So this is output. You can see 499.15 millivolt. This is what I have. This is the gain, 499.15 divided by 200, which is 2.49. This is what we are expected over here. This is what is 2.49. And what actually the R out is actually 249. So that you will get it. See here again, go back to this simulation. Maybe you can take out the input now. Okay, what I'll do is let me delete this. Now this is the output peak to peak when RL is in, okay, like 10 mega ohm. Just come over here, use the arrow key, it will come to second plot. You can see now this is half of that, almost close to that. Okay, you had it as 499. This is almost close to, this would have been 240. Okay, 248. No, this is, the resistance is slightly around 250 ohms. So this is how you are getting the resistance as 250 ohm as expected. So as expected here. So this is R out is 249 ohms. Okay, now let us see the next circuit. Now the gain is totally, load is totally different. You can see now this is R02 plus R03 into 1 over GM to R02. So this is, of course, these are the specifications as in the previous case. We have the W bell of this as, again, as in the previous case, 247. Now you need to slightly understand this one. So the DC voltage here is 0.9 and the DC voltage here should be half of this, because from here to here it is 0.9. So let us have 0.45 less than this, or 0.45 more than, sorry, less than 1.8. So VDS of this M3, VDS of this M2, we want it to be 0.45, that is half of 0.9. So that's why the DC voltage of this is 1.35. The DC voltage at this point is 0.9. So that's why you can see the VDS of M3 and M2 is equal to 0.45 volts, and VDS of M1 is actually 0.9. So you got this as 247.7 when this VDS is 0.9. Now to find the W bell of this transistor and this transistor, in this VDS I am substituting 0.45, and VGS is still I want to have it as 0.9. So upon doing all these things, I got a ratio of both the transistor as 497.7. So the dimension of both the transistor is given by this. And once I know what is the dimensions, now I should fix the bias voltages, VB1, VB2. So what is this VB1? So this is actually the drain, this is actually gate, this is source. So now this is source, this is gate. So I should have minus 0.6 here. Since it is 1.8, if I make it 1.2, then it is minus 0.6. Here you have it as 1.35, and this should be 0.6 times, or 0.6 lesser than this, 0.6 less than this. So that's what is this you have. Can you see now? VGS3 is equal to VGS2 is equal to minus 0.6. VGS3 is actually this value. So I think you are getting what I'm trying to say here. Let me just show you both of them simultaneously so that you will get the idea. This is what I am trying to show now. Okay, here. see now. So this is what is VGS3 is. This is VGS3. This VGS3 is actually equal to, of course, required voltage is minus 0.6. Is it not equal to what is VG now? The VG of this is gate voltage, that is VB2. What is VS of this? Is the VS of that equal to VDD? So that's why it is VB2 is 1.2 volts. So I'll be connecting 1.2 over here. Can you see this is 1.2 volts? Can you see? Oh, sorry. Let me just open that. That is, I think, fourth one. Not fourth. Is it fourth? No, this is a different one. Let me open. Not this. Okay, this is actually PMOS, sorry, NMOS one. Let me see where is that PMOS wala. Okay, this is, no, this, just a minute. No. Okay. Where is fourth? Oh, this is fourth. I was actually opening the fifth one. See now, is this 1.2 as expected over here? So this is at 1.2 volt. What is this voltage? Can you see this is 0.75? This is 0.75. So I am having it as 1.2. So this is 1.8. So that VGS becomes minus 0.6. This is at 1.35 volts. So this is at 0.75. Again I have a VGS of minus 0.6. So you have to be a bit careful in adjusting the voltages of this bias voltage, by knowing the source voltage as 1.8, by fixing the source voltage as 1.35. So how does this become 1.35? Because I know that this is 0.9, because this is 1.8. My output voltage should be half of VDD. So this 0.9 volt is divided equally between this and this transistor. That's why it is 0.45 here, 0.45 there. So 0.9 plus 0.45 is 1.35. So 1.35 minus 0.75 is equal to minus 0.6. So that's what is the bias voltages of these two transistors. So that's what is here. You can see now the gain. So gain expression is GM1 R01 parallel with this, and R out is this. From these values, of course, take time to understand each and every values of this. So now you can see the gain happens to be 990. So it's a huge gain because you have a cascaded load. Load is cascaded. Now it is this, and of course R out comes to be 99 kilo ohm. So that's why you can see I have made the resistance initially 10 mega ohm. The second resistance is made equal to 99k here, so that I will see the output voltage maximum with a gain of 990, and for the second case, so the output voltage will be half of the previous one because you are connecting this equal to R out of that. So let me do the simulation now. Of course, it takes for you to understand all these things. So you know this expression, get the values of all resistances and GM. You can verify all these R01, R02, R03, which is 1 over GDS from the dot DC analysis. You can go to this view and then see this. Of course, you have to do dot DC. How do you do dot DC? It is here. Do dot DC and then see all these GDS values. Okay, I should actually, that was not pasted. I should paste it here. Let me run. Okay, let me just remove all of them. Too many files. I'll just take out this also. This. Now let me see. Of course, you can verify what is the voltage here. Can you see the DC voltage is 0.9 almost? Can you see it's almost at 0.9? And what is the voltage here? voltage here has to be 0.45, that is 1.35. Can you see this voltage 1.35? Now if you actually see the VGS of this will be minus 0.6. Can you see this is minus 0.6, this is 0.6, and can you see this voltage is also close to that? Can you see this now? That's also 0.6. So of course why it is coming as positive is because I am making VSG, that is source and gate. If you do gate source, it will be minus. Now what all assumptions what all requirement we expected, we are all getting, because I have substituted the dimensions as expected. So these dimensions you can just see here, verify that, and let us do the dot tran. How do I do dot tran? So let me just take out that and then put a dot. I'm doing dot tran. Let me run now. Now let me take out everything except the output. I'll take out this, take out this, take out this. Let me also see the input, because I have to measure the gain. So gain happens to be 990. So let us find out what is the gain. So for that let me put a different pane. This is my output. Let me measure what is input peak to peak. So input peak to peak, as I know that, okay, input peak to peak is how much? See this, it's actually 0.2 millivolt, that is 200 microvolt. So that's what you are seeing. So let me go here, zoom it. This is not required. Let me just do this. Keep one cursor here. Okay, double click on this. I'll get one more cursor. This is let me first do it on the input. Input is known to be 200 microvolt now. Is it there? Can you see it's almost 200 microvolt, 199.1. Let us see the output. So let me measure, let me note down V0 peak to peak by V in peak to peak. V in peak to peak was 200 micro. What is V0 peak to peak? V0 peak to peak, if you can see there, it is 198.78 millivolt. See this? See these values? This is 200 microvolt. This is 198.78 millivolt. So you can, this is milli, this is micro. This is 198.78 exponential minus 3 divided by 200 exponential minus 6. This is my expression or the ratio. Can you see it is 993.9 volt per volt. This is the gain of the amplifier. This is what is expected. How much you expected? You expected a gain of 990. So are you not getting a gain of close to that, 993? And how about R out? R out happens to be 99 kilo ohm. So if you see in the circuit, where is the circuit? So if you see the circuit, the first resistance is very large. The second resistance I kept it equal to R out, which is 99k. So my output will be half of this 198 point something. I'll go back to my waveforms. Okay, let me just take out this pane. Okay, let me just take out this input also. Now if I come here and then find out what is this. See now, am I there at the peak to peak of this? Yes, I'm almost there. I had it as just let us see. This is actually 99.61 millivolt. Compare that with this. Okay, let us see here. I had earlier 198.78 millivolt with RL as 10 meg. Can you see now when I reduce the RL to 99k, has it now almost become half of that? This is 198.78 divided by 2. Can you see it is 99.3? So do you have that voltage? Is it 99.61 millivolt? Which means that the resistance that I have connected here, which is 99k, is equal to the R out of the amplifier. Okay, this way you can able to do it for other circuits also. I have shared all the circuits. So this is also there. Now you can see this is slightly different now. So you don't have R0, you have a 1 over GM3. You just do the design of all these things, understand the design, find the expression for this one. Now you can see R out becomes 66.6. Now the gain will become 666. You can verify all these. You can see one more thing where you have a NMOS load, the gain becomes very less, so which is almost equal to 1 now. This gain is close to 1 because GM1 is equal to GM2. You'll get a gain equal to almost close to 1. Suppose if I'm correct, okay, you'll get a gain of close to 1. And this is one more circuit, so where I just intentionally put this 300 ohm. Now it is in series with this. This gain comes out to be 3.82. So I want each one of you to just understand this, spend time on this. You have to calculate on your calculator. You have to get all these values and then see the simulation results. So it's worth spending some time on simulating and verify the values of each of the bias voltage, this VDS, this VGS, so that it should tally with your paper design. So thank you so much for watching this.